Our universe is built on a secret code of perfect mathematical balance. This code is symmetry, the silent architect behind everything from spinning galaxies to the smallest particles. By the end of this journey, you will see the cosmos not as a chaotic accident, but as a breathtakingly elegant and interconnected whole. We will uncover why the afterglow of the Big Bang looks the same in every direction, and how a single mathematical theorem written a century ago ties the entire universe together. What hidden order do you see when you look up at the night sky? Look closely at a single snowflake, its delicate six-pointed pattern repeating with flawless precision. This miniature masterpiece is a whisper of a far grander truth, a tiny echo of the universe's own deepest structural principles. We call this cosmic symmetry, and it is far more than just a pleasing visual balance. It is the set of invariant properties, the unchanging rules and balanced forms that persist across the unimaginable scales of space and time. These symmetries are the fundamental laws written into the fabric of reality itself, dictating everything from the graceful ellipse of a planet's orbit to the furious fusion that forges the elements inside stars. The physicist Brian Greene captured this idea perfectly when he said, "Symmetry is the theme nature most loves to repeat. This is not poetry, it is practical physics." Symmetry is the most powerful tool scientists have for uncovering the rules of the cosmos. For example, the simple fact that the laws of physics do not change from moment to moment, a symmetry of time, leads directly and mathematically to one of our most cherished laws, the conservation of energy. It is a profound connection, a hidden link between an abstract principle and a concrete rule that governs every interaction in the universe. Look up at the night sky. To the ancient astronomers, the stars seemed evenly scattered, a suggestion of a balanced and structured cosmos. That initial, intuitive observation of symmetry was a first step on a long journey. It led to the realization that the gravitational field around a star or planet possesses a beautiful rotational symmetry, which in turn explains why orbits take their predictable, elliptical shapes. This symmetry allowed Isaac Newton to unite the physics of the heavens and the earth, revealing one universal law. But what if the symmetries we can easily see and measure, like the rotation of a planet or the flow of time, are just surface level? What if they are fragments, broken pieces of a more profound and hidden order waiting to be decoded? This compelling question drives us toward the first monumental discovery that truly began to crack open the cosmic code. That faint, uniform hiss from the sky was no instrument malfunction. It was the echo of creation itself, a whisper from the very edge of time. In the 1960s, astronomers Arno Penzias and Robert Wilson were calibrating a sensitive radio antenna, trying to eliminate a persistent background noise they could not explain. What they had stumbled upon was the cosmic microwave background, the cooled and stretched afterglow of the Big Bang, bathing the entire universe in a sea of ancient light. Its most profound feature was not its existence but its symmetry. This light, our oldest photograph of the cosmos, was almost perfectly uniform in every direction. This property, called isotropy, means the early universe looked the same no matter where you were or which way you turned. The temperature of this primordial glow was balanced to an astonishing degree, with variations so tiny they measure only about 1 part in 100,000. Imagine a sphere the size of Earth with its highest mountain and deepest ocean trench, differing in height by less than the thickness of a sheet of paper. That is the scale of the smoothness we are talking about. This discovery was a monumental validation of the cosmological principle, the idea that on the largest scales, the universe is both homogeneous, meaning matter is evenly distributed, and isotropic, meaning it has no special direction. It told us that our cosmic home had no center and no edge in the way we intuitively understand them. the universe was born in a state of near-perfect balance, a symmetrical seed from which everything we see would eventually grow. But perfect symmetry is a static thing. If the early universe had been completely smooth, we would not be here to observe it. There would be no galaxies, no stars, no planets, just a thin, cold, and uniform fog of particles stretching forever. The magnificent structures we see today, from glittering spiral galaxies to vast cosmic webs, required that initial symmetry to break just slightly. Those 1 in 100,000 temperature fluctuations imprinted in the cosmic microwave background were the crucial imperfections, the cosmic seeds of all structure. They were tiny pockets of slightly denser matter, gravitational anchors that, over billions of years, pulled in surrounding gas and dust to form the first stars and the grand architectures of galaxies. Missions like the Cosmic Background Explorer and later the Planck Space Telescope have painstakingly mapped these fluctuations, creating a detailed baby picture of the universe that reveals the precise blueprint for its future growth. So this first great discovery presents us with a beautiful cosmic duality. The large-scale symmetry of the cosmic microwave background reveals a universe born from a state of elegant, balanced simplicity. Yet it is the subtle breaking of that same symmetry, those minute wrinkles in the fabric of space, that gifted the cosmos with its rich complexity and ultimately with us. It is a reminder that symmetry is not an end state, but a dynamic starting point, a set of perfect conditions from which diversity can emerge. This understanding of the universe's large-scale symmetry naturally leads us to ask a deeper question. What are the fundamental rules, the invisible forces that orchestrate this grand, balanced expansion from a single point to the vast cosmos we inhabit today? The subtle imperfections in the cosmic background were the seeds of all structure, but what guaranteed that the universe would follow a consistent set of rules as it grew from that seed? The answer lies not in a force but in a principle, a connection so elegant it reshaped physics forever. In the early 20th century, while the scientific world was captivated by Einstein's relativity, a brilliant mathematician named Emmy Noether was working quietly in Germany, often facing significant professional barriers. Her groundbreaking insight, now known as Noether's theorem, revealed a breathtaking link between the abstract beauty of symmetry and the concrete laws that govern motion. She proved with mathematical certainty that for every continuous symmetry in nature, there is a corresponding law of conservation. This is a concept of staggering power. Think of it as the universe's ultimate accounting system. The fact that the laws of physics do not change from one moment to the next, a symmetry in time, means that energy must be conserved. It cannot be created or destroyed, only transformed. The fact that the laws of physics are the same here as they are a mile away, a symmetry of space, means that momentum must be conserved. And the fact that the laws of physics are the same no matter which direction you face, a symmetry of rotation, means that angular momentum is conserved. This last one gives us a perfect, everyday example. A figure skater spinning on the ice pulls their arms in close to their body. They are not pushing off the ice to spin faster. They are simply utilizing the conservation of angular momentum. Their rotation speeds up because the distribution of their mass changes, but the total rotational momentum, governed by that underlying symmetry, remains constant. Noether's theorem did more than explain familiar phenomena. It provided the deep mathematical reason why certain quantities, like electric charge, are always conserved in an isolated system. These are not arbitrary rules imposed on the universe. They are direct, unavoidable consequences of the universe's inherent symmetrical structure. Her work became the silent backbone of modern physics, indispensable for developing quantum field theory and the standard model of particle physics. The profound implication is this: the very predictability of the cosmos, the reason experiments are repeatable and the future is not entirely random, relies on these hidden symmetries. They are the unwavering framework upon which all physical law is built. This revelation forces us to look at the stage itself, not just the actors upon it. If symmetries dictate the conservation laws that govern matter and energy, what does that tell us about the nature of the stage, the very fabric of space-time? Albert Einstein's revolutionary insight began not in a grand observatory, but in a quiet patent office, his mind tracing the path of a light beam. He realized a profound and unsettling symmetry. The laws of physics must look identical to all observers moving at a constant velocity. This principle, called Lorentz invariance, is the bedrock of his special theory of relativity. It states that the fundamental equations describing reality do not change or are invariant under rotations or boosts in the four-dimensional fabric of spacetime. The most famous consequence of this symmetry is the absolute, unchanging speed of light. No matter how fast you are moving toward or away from a light source, you will always measure its speed as the same constant value. This single, stubborn fact forces time and space to lose their independent, absolute status. Instead, they weave together into a single flexible continuum where time can dilate, stretching out for a moving observer, and lengths can contract, all to preserve that ultimate cosmic speed limit and the symmetry of the laws. Think of it as the universe's ultimate rulebook, one that remains perfectly consistent for every player, regardless of their motion. This was a shattering departure from Newton's world of absolute space and time. It was not a wild guess. Experiments had already pointed the way. The famous Michelson-Morley experiment of the late 19th century sought to measure the Earth's motion through a hypothetical medium for light waves called the luminiferous ether. Their meticulous measurements found nothing, no ether wind, no preferred frame of reference. The speed of light was simply constant. Einstein's genius was to take this puzzling experimental result not as a problem, but as a foundational principle, a clue to a deeper symmetry in nature. This symmetry does more than reshape our abstract understanding. It operates in the technology we use every day. The global positioning system in your phone or car relies on ultra-precise atomic clocks aboard satellites. Because those satellites are moving at high speeds relative to the Earth's surface, relativistic time dilation, a direct result of Lorentz invariance, causes their clocks to tick at a slightly different rate than clocks on the ground. If engineers did not correct for this symmetrical effect of spacetime, GPS coordinates would drift by several miles each day, rendering the system useless. From the subatomic particles zipping through cosmic rays to the vast scales of cosmology, Lorentz invariance ensures a consistent reality. It is the reason a physicist in a lab and an astronaut on a high-speed journey can use the same equations and trust they describe the same universe. This elegant spacetime symmetry set the stage for an even more mysterious domain, where the rules of the large and the small would meet in a dazzling and often perplexing dance. Yet the elegant symmetry of spacetime was about to collide with a far stranger reality. Beneath the smooth, predictable stage of relativity lies the quantum world, a realm of probability clouds, ghostly entanglements, and particles that can be in two places at once. To bring order to this chaos, physicists uncovered a symmetry so fundamental it is woven into the very mathematics of reality itself. It is called CPT symmetry, and it is the ultimate cosmic reset button. C stands for charge conjugation, which swaps every particle with its antimatter counterpart, turning an electron into a positron. P is parity, which mirrors all spatial coordinates, flipping left for right as if looking into a perfect looking glass. T is time reversal, running the clock backwards on any process. The astonishing claim of CPT symmetry is this: if you perform all three operations together, simultaneously reversing charge, mirroring space, and reversing time, the universe should obey exactly the same laws. It is as if you took a film of any interaction in nature, replaced every particle with its antimatter twin, viewed it in a mirror, and then played the film in reverse. According to this profound symmetry, that reversed, mirrored antimatter movie would be completely indistinguishable from the original. This is not just a curious idea, it is a cornerstone of modern quantum field theory, the framework that successfully merges quantum mechanics with special relativity. Its discovery emerged from deep theoretical work in the mid-20th century, revealing that CPT invariance is required for our description of particles and forces to be logically consistent. This symmetry makes a powerful and testable prediction. A particle and its antiparticle must have exactly the same mass and the same intrinsic lifetime. Imagine two perfectly matched cosmic clocks, one made of matter and one of antimatter, ticking down toward their decay at precisely the same rate. Incredibly precise experiments have confirmed this, for instance, comparing electrons and their antimatter twins, positrons, to phenomenal levels of accuracy. But the story grows more intriguing because the individual components of this symmetry are not always respected. Nature, it seems, has a slight bias. In the 1950s, physicist Qin-Sheng Wu and her colleagues conducted a landmark experiment involving the decay of cobalt-60 atoms governed by the weak nuclear force. They found that the decay did not look the same in a mirror. The parity, or P, symmetry was violated. Later, it was shown that the combined operation of charge and parity, CP, could also be violated in certain particle decays. This means if you just swapped matter for antimatter and looked in a mirror, the process might look slightly different. Yet, when you add the final step of reversing time, the full CPT symmetry always holds firm. It is as if the universe allows for individual asymmetries, small biases in charge, mirroring, or time's arrow, but demands perfect balance when all three are combined. This restoration of balance has a staggering implication for the origin of everything. CPT symmetry suggests that in the fiery first moments of the Big Bang, matter and antimatter should have been forged in perfectly equal amounts. But if that were true, they would have annihilated each other completely upon contact, leaving behind a universe of pure energy with no atoms, no stars, and no us. The fact that we exist in a cosmos dominated by matter is one of physics' greatest unsolved mysteries. It tells us that somewhere, somehow, a tiny crack in the perfect symmetry of the early universe favored matter over antimatter, allowing a precious remnant to survive and build everything we see. So CPT symmetry serves as both a guardian of cosmic law and a signpost to a deeper mystery. It binds the quantum world to the relativistic one, ensuring the mathematical consistency of reality itself, while its near-perfect balance points to a moment of profound imbalance at the dawn of time. This deep connection between symmetry and the forces that sculpt our universe leads us to ask, how do these fundamental forces themselves arise from symmetrical principles? The perfect balance of CPT symmetry points to a deeper layer of cosmic order, one where the forces themselves are not arbitrary commands but elegant consequences of a hidden rule. This rule is gauge symmetry, and it is the master weaver of reality's tapestry. Imagine a vast, invisible field stretching across the universe, like an ocean whose currents influence everything within it. Now imagine you have the freedom to adjust the phase, the rhythm or timing of that field at every single point in space, independently, without changing the underlying physics. This freedom, this local symmetry, is the essence of gauge invariance. It is a demand that the laws of nature must remain unchanged even when we perform these intricate, location-specific adjustments. This might sound like an abstract mathematical game, but its consequences are breathtakingly concrete. The universe, it turns out, enforces this local symmetry by generating force-carrying particles that mediate interactions between matter. In the 1950s, physicists Chen-Ning Yong and Robert Mills formalized this profound connection, showing how specific gauge symmetries mathematically necessitate the existence of fundamental forces. Their work laid the foundation for the Standard Model of particle physics, our most successful map of the subatomic world. Consider the familiar force of electromagnetism. It arises from a U1 gauge symmetry, which is essentially the freedom to change the phase of an electron's quantum field. To preserve the laws under this local adjustment, nature must introduce a compensating field, the electromagnetic field, whose particle is the photon. This elegant requirement gives us both the conservation of electric charge and the particle of light itself. The photon is a gauge boson, a messenger particle born directly from symmetry. This pattern repeats for the other forces. The strong nuclear force which glues quarks together inside protons and neutrons comes from a more complex SU3 gauge symmetry, giving us 8 different types of gauge bosons called gluons. The weak nuclear force responsible for certain types of radioactive decay arises from an SU2 symmetry, producing the W and Z bosons. In this framework, particles of matter like electrons and quarks are like actors on a stage, while the gauge bosons are the very fabric of the stage, responding instantly to the actor's movements to keep the script, the laws of physics, consistent everywhere. But a puzzle remained. If gauge symmetry is so perfect, why do the W and Z bosons have immense mass while the photon is massless? This is where the story takes a brilliant turn with the Higgs mechanism. In the early universe, a field now called the Higgs field permeated all of space with a non-zero value. This configuration broke the perfect symmetry between the electromagnetic and weak forces, a process known as electroweak symmetry breaking. Yet, crucially, the underlying gauge symmetry of the laws was preserved. Think of it like a marble resting at the very peak of a perfectly symmetrical hill, a point of unstable symmetry. When it rolls down into the surrounding valley, it picks a specific direction, breaking the rotational symmetry of the hilltop. But the law of gravity itself, which caused the roll, remains perfectly symmetric. The Higgs field's roll into its stable state gave mass to the W and Z bosons, while leaving the photon massless, effectively separating the unified electroweak force into the 2 distinct forces we see today. Other particles, like electrons and quarks, acquire their mass by interacting with this omnipresent Higgs field. The triumphant confirmation of this mechanism came in 2012 with the discovery of the Higgs boson at the Large Hadron Collider, a ripple in the Higgs field that proved its existence. Gauge symmetry, therefore, provides a staggering mathematical elegance, unifying 3 of the 4 fundamental forces under a single conceptual umbrella. It reveals that forces are not primary but secondary, emerging from the universe's deep-seated need for local consistency. This leaves gravity, described by Einstein's general relativity, as the final puzzle, the one force not yet woven into this symmetrical tapestry. As we marvel at this subatomic symmetry, our gaze is pulled upward to the colossal structures these very forces have built across the cosmos. The universe's earliest sound waves are still echoing around us. In the fiery first few 100,000 years after the Big Bang, the cosmos was not a serene void but a seething, opaque plasma, a thick soup of particles and radiation tightly coupled together. Within this primordial fluid, a battle raged. Gravity, relentlessly pulling matter inward, fought against the immense outward pressure of radiation. This conflict created ripples, vast spherical pressure waves that surged outward through the plasma at nearly 2/3 the speed of light. These are the Baryon acoustic oscillations, and they are the universe's first and most enduring drumbeat. Then, around 380,000 years after the beginning, the universe cooled enough for electrons and protons to combine into neutral hydrogen atoms. In a cosmic instant known as recombination, the fog cleared, and radiation could travel freely, becoming the cosmic microwave background we observe today. More importantly, those raging sound waves froze in place. The waves stopped propagating, leaving their imprint as a subtle, spherical shell of slightly denser matter surrounding every initial gravitational seed. Think of it like a raindrop falling into a still pond. The initial splash is the dense seed of a future galaxy, and the ripple expanding outward is the acoustic wave. When the pond suddenly freezes solid, the ripple is captured forever as a frozen ring around the splash. In the universe, that frozen ring has a very specific size, determined by how far sound could travel in that hot plasma before the moment of recombination. That distance is about 500 million light-years. For billions of years, gravity pulled on these imprints, drawing in more matter to form galaxies and clusters. The result is a breathtakingly symmetric pattern etched across the cosmos on the largest scales. When astronomers create three-dimensional maps of millions of galaxies, like those from the Sloan Digital Sky Survey, they find a subtle but statistically undeniable signal. There is a slight excess of galaxy pairs separated by that same 500 million light-year scale. It is as if the universe is studded with countless invisible spheres of this precise size, with galaxies tending to form on their surfaces. This pattern is a fossilized symmetry from the universe's infancy, a standard ruler etched into the fabric of space itself. Because we know the ruler's true size from physics, we can measure how it appears stretched or compressed at different distances, and thus at different epochs in cosmic history. This allows us to measure the expansion rate of the universe with extraordinary precision, completely independent of other methods like supernova. The measurements from Baryon acoustic oscillations have become one of the strongest pillars of evidence for our current cosmological model. They confirm the existence of dark energy, the mysterious force accelerating the expansion, and they tell us the universe is geometrically flat on large scales, just as predicted. It is a form of cosmic echolocation, using the faint echo of primordial sound to map the shape and fate of everything. This grand, spherical symmetry in the distribution of matter, a direct relic of the universe's hot, dense youth, provides a steady heartbeat against which we can measure the cosmos' growth. From this vast, fossilized echo spanning hundreds of millions of light-years, we now turn inward to the symmetries that govern the smallest building blocks of that very matter. The frozen echoes of the universe's first sound gave us a ruler spanning hundreds of millions of light-years. But to understand the matter that ruler measures, we must descend into the quantum arena, where particles are sorted into two cosmic tribes by a law of breathtaking elegance. This is the spin statistics theorem, a discovery that links a particle's intrinsic spin to its very identity and behavior, a symmetry so fundamental it makes stable matter possible. Every fundamental particle possesses a property called spin, a form of intrinsic angular momentum that is quantized, meaning it comes in discrete units. It is tempting to picture a tiny spinning ball, but that analogy fails. Spin is a purely quantum mechanical trait, more like an innate orientation or a fixed amount of rotational charge. The spin statistics theorem, emerging from the marriage of relativity and quantum mechanics in the work of Wolfgang Pauli and others, makes a profound declaration. Particles with half-integer spin, like 1/2, 3/2, and so on, are called fermions. Electrons, protons, and neutrons are all fermions. Particles with integer spin, like 0, 1, 2, are called bosons. Photons and the Higgs boson are in this family. This classification is not just a label, it dictates the particle's entire social behavior through quantum statistics. Fermions are the ultimate individualists governed by the Pauli exclusion principle. No two identical fermions can occupy the same quantum state at the same time. Think of it as a cosmic rule against overcrowding in the quantum world. Bosons, in stark contrast, are the ultimate collectivists. They happily crowd into the exact same quantum state, a phenomenon called Bose-Einstein condensation. The theorem reveals a deep and necessary symmetry. The connection between a particle's spin and its statistical behavior is not accidental but mandatory for a logically consistent universe that includes special relativity. This symmetry has universe-building consequences. Because electrons are fermions, they stack into distinct shells around an atomic nucleus, following the Pauli principle. This is the sole reason for the structure of the periodic table of elements and the diversity of chemistry. Without this fermionic exclusivity, all electrons would collapse into the lowest energy state, and atoms as we know them, along with all of chemistry and life, would simply not exist. Bosonic sociability, on the other hand, enables the transmission of forces and remarkable collective phenomena. Photons, the bosons of light, can all occupy the same state, which is precisely what makes a laser possible, a coherent beam where light waves march in perfect lockstep. In laboratories, scientists have cooled clouds of atoms to temperatures a whisper above absolute zero. There, rubidium atoms, which behave as bosons, lose their individual identities and merge into a single quantum wave, a Bose-Einstein condensate, a direct and spectacular confirmation of this statistical symmetry. This fundamental distinction, rooted in the deep symmetry of the spin-statistics connection, shapes reality at every scale. It explains why matter is solid and stable, thanks to fermionic repulsion. And in the extreme cores of collapsed stars, it is the Pauli exclusion pressure between neutrons, another fermionic effect, that holds up neutron stars against the crushing force of their own gravity. From the architecture of an atom to the fate of a star, the universe is built upon this elegant quantum divide. As we marvel at how symmetry dictates the social rules of particles, we can see a similar, tangible order in the world around us, in the perfect, repeating lattices of crystals and the materials they form. The same elegant rules that govern particle behavior also sculpt the tangible world in our hands. Look at the perfect facets of a diamond or the intricate branches of a snowflake, and you are witnessing a direct translation of cosmic symmetry into solid form. These repeating, orderly patterns are the domain of crystallographic symmetry groups, the mathematical blueprints for every crystal in existence. In the early 20th century, Max von Laue made a breakthrough discovery by shining X-rays through a crystal. The resulting diffraction pattern, a beautiful array of dots, was not random scatter but a precise mathematical fingerprint. It revealed that crystals are not just orderly, they are three-dimensional lattices, perfectly repeating arrangements of atoms stretching in all directions. Crystallographic symmetry groups classify these lattices by describing all the rotations, reflections, and translations you could perform that would leave the crystal looking exactly the same. A cube, for instance, can be rotated 90 degrees around certain axes and still appear unchanged, a symmetry that defines the cubic crystal system to which diamonds and common salt belong. A snowflake exhibits hexagonal symmetry based on 60-degree rotations. These are not just abstract labels, they are the very source of a material's physical properties. The incredible hardness of a diamond arises directly from the strength and symmetry of the carbon bonds in its cubic lattice. The piezoelectric effect in quartz, where squeezing the crystal generates a small electric voltage, is a direct consequence of its specific, non-centrosymmetric structure. When pressure distorts that lattice, the symmetry is momentarily broken in a way that separates positive and negative charges, creating voltage. This deep link between form and function extends to a crystal's electronic band structure, which determines whether it is a metal, an insulator, or a semiconductor. The allowed energy levels for electrons within the crystal are sculpted by the invariances of the atomic lattice, a perfect example of how spatial symmetry dictates function. The mathematical pursuit of these patterns led to a stunning triumph of classification. in 3 dimensions, there are exactly 230 distinct ways to arrange atoms in a perfectly repeating, symmetric pattern. These are the 230 space groups, a complete catalog of every possible crystalline symmetry that can exist in our universe. This knowledge is the foundation of modern material science and nanotechnology, allowing us to engineer substances with desired properties by designing their symmetrical underpinnings. Sometimes the most useful properties emerge not from perfect symmetry, but from its deliberate breaking. In ferroelectric materials, tiny regions called domains have their electric polarization aligned in different directions. Applying an electric field can flip these domains, breaking the local symmetry and creating a material with a permanent, switchable electric field, crucial for memory chips in electronics. This dance between perfect crystalline order and controlled symmetry breaking is what gives us the technological world we inhabit, from silicon chips to laser crystals. And if such precise geometric order can arise from the chaotic dance of atoms cooling into solids, it invites a staggering question. Could similar principles of symmetry and pattern formation be written across far vaster scales, in the architecture of solar systems and galaxies themselves? The symmetrical lattices of crystals reveal a universe that loves to repeat itself. But what about the grander architectures, the vast orbital systems circling distant suns? In the 1700s, astronomers gazing at our own solar system noticed something intriguing, a pattern in the emptiness. The planets did not orbit at random distances. They seemed to follow a rough, rhythmic spacing from the sun. This observation was codified into what became known as the Titius-Bode law, an empirical rule that predicted a planet's distance based on a simple mathematical sequence. Starting with Mercury, if you took a series of numbers, added 4 to each, and then divided by 10, you got a remarkably close match to the actual orbital distances known at the time. The pattern suggested a logarithmic symmetry, with each successive planet's orbit being roughly twice as far from the Sun as the one before it. It was as if the solar system had been constructed with a cosmic ruler, marking positions at regular intervals. This perceived pattern was not a strict law of physics, but its allure was undeniable. It famously inspired the search for a missing planet between Mars and Jupiter, a search that led to the discovery of the asteroid Ceres in 1801, the first member of what we now call the asteroid belt. The law's success for the inner planets felt like a triumph of cosmic order, a hint at some deep, hidden symmetry governing the formation of planetary systems. Yet, like many first attempts to map the universe's design, the Titius-Bode law eventually showed its cracks. It failed to accurately predict the orbits of the outer giants Neptune and Pluto, revealing it to be more of a suggestive trend than a fundamental rule. Modern astronomy understands that planet formation is a messy, dynamic ballet of gravity, collision, and migration within a swirling protoplanetary disk of gas and dust. While no single simple formula dictates final orbits, sophisticated computer simulations show that gravitational interactions between forming planets and the disk itself can indeed produce semi-regular spacing. Planets often push each other into stable, resonant orbits where their orbital periods form simple ratios like 2:1 or 3:2, preventing chaotic collisions. This natural sorting, driven by symmetry seeking gravitational dynamics, can create the kind of orderly progression that the Titius-Bode law approximated. So while the specific mathematical rule may have been a fortunate coincidence for our particular solar system, the broader insight endures. The human mind, detecting a hint of pattern, was drawn to a deeper truth that the chaos of creation often settles into states of balanced symmetry. The quest it sparked led directly to new discoveries, proving that even an imperfect map can guide us to real treasure. This instinct to find order in the celestial expanse now lifts our gaze from the scale of solar systems to the majestic, spinning symmetries of islands in the sky, the galaxies themselves. A spiral galaxy is a whirlpool of stars, a vast pinwheel spinning in the dark. Its arms do not trail behind like smoke from a moving train. They are density waves, great rotating patterns of compression that move through the galactic disk like sound waves through air. As stars and gas clouds orbit the galactic center, they enter these slow-moving waves, their motion briefly slowed and compressed, triggering the brilliant bursts of star formation that light up the spiral arms. The galaxy is a dynamic, living structure, its symmetry one of motion and pattern, not of static arrangement. This elegant concept, pioneered by astronomers like Bertil Lindblad and later refined by others, explains a beautiful paradox. The spiral arms we see are not permanent fixtures made of the same stars. They are traffic jams in the stellar flow, a rotating pattern through which individual stars pass in and out over hundreds of millions of years. This grand design is sustained by gravity, a self-reinforcing dance where the gravitational pull of the arms themselves helps maintain the wave pattern. The underlying stability for this delicate balance comes from two profound sources. First, the conservation of angular momentum. That same symmetry principle from Noether's theorem ensures the overall rotation of the galactic disk. Second, and crucially, the immense invisible halo of dark matter that surrounds every large galaxy provides a gravitational scaffold. This unseen ocean of matter holds the luminous disk within its embrace, preventing the spiral pattern from winding up too tightly and dissolving into chaos over cosmic time. Look at a galaxy like the Whirlpool Galaxy, and you witness this symmetry in its most pristine form. Its two sweeping arms are nearly perfect mirror images, a bilateral symmetry in its lanes of dust and glowing pink star-forming regions. Yet this stunning order is not born in isolation. It is enhanced by a gravitational tug-of-war with a smaller companion galaxy, its gravity delicately stirring the disk and amplifying the spiral pattern. Here, interaction does not destroy symmetry, it sculpts it, revealing how dynamics and design are intimately intertwined on the grandest scales. This galactic order, written in starlight, is just one language of the cosmos. To understand the universe more deeply, we must learn to read another, the symmetrical messages encoded in the very radiation that illuminates these celestial wonders. A perfectly enclosed oven, glowing from heat alone, holds a secret about the nature of light itself. Inside such a cavity, radiation bounces endlessly off the walls, reaching a state of perfect balance with the material, a condition known as thermal equilibrium. In this state, the radiation achieves a profound symmetry. It becomes isotropic, meaning it streams equally in all directions, and homogeneous, meaning its properties are uniform throughout the space. The energy it emits forms a smooth, predictable curve across all wavelengths, a universal fingerprint called the Blackbody spectrum. In the year 1900, Max Planck wrestled with the mathematics of this curve, and in a move of sheer brilliance, he proposed that energy could only be emitted or absorbed in tiny, discrete packets, which he called quanta. This was the birth of quantum theory, and the Blackbody spectrum was its first great triumph. The shape of that curve, described by Planck's law, depends on one thing and one thing only: temperature. It does not matter if the cavity is made of iron, ceramic, or diamond. At the same temperature, the radiant energy inside will always arrange itself into that same perfect, symmetrical curve. This is the symmetry of thermal equilibrium, a universal language of heat and light. Now, lift this concept from a laboratory oven to the cosmos itself. The cosmic microwave background, that ancient afterglow from the dawn of time, is the most perfect blackbody ever measured. After traveling for over 13 billion years, the radiation from the early universe has cooled to just a few degrees above absolute zero, but it has retained that pristine equilibrium form. This is not a trivial detail, it is a monumental confirmation of the hot Big Bang model. It tells us that the infant universe was once a seething, opaque plasma in a state of near-perfect thermal equilibrium, where matter and radiation were so thoroughly mixed that they achieved a uniform temperature everywhere. Missions like the Cosmic Background Explorer satellite did not just detect this background glow, they measured its spectrum with almost unbelievable precision. The data points fit the theoretical Blackbody curve so perfectly that the deviations are less than 1/100th of 1%. It is a match made in heaven, literally, a direct observational echo of that symmetrical state from which everything emerged. This cosmic symmetry grants astronomers a powerful tool, a universal thermometer. By measuring the precise temperature of the Blackbody spectrum in different directions, scientists can detect the faintest of variations, those 1 part in 100,000 wrinkles that seeded all cosmic structure. The profound uniformity of this background temperature across the sky is our strongest evidence that the universe began in a state of magnificent, balanced simplicity. From this deep thermal symmetry of the past, our story now turns toward a mysterious force that is shaping the future, breaking the symmetry of a static cosmos and driving it apart at an ever-increasing pace. Einstein's greatest blunder was, in the end, a glimpse of the future. When he introduced the cosmological constant into his equations of general relativity, he did so to keep the universe static, a fixed stage for the drama of matter. He later called it his biggest mistake, but the cosmos had the last laugh. The cosmological constant, or something remarkably like it, is real. It is the simplest manifestation of dark energy, a uniform energy density woven into the very fabric of empty space itself. Its effect is to give spacetime a gentle, repulsive push, causing the expansion of the universe not just to continue, but to accelerate. This leads us to a profound and hauntingly beautiful model of cosmic geometry called de Sitter space. Imagine a universe utterly empty of stars, galaxies, or any matter at all, yet filled with this constant dark energy. In such a place, space-time would not just expand, it would expand exponentially, with every region of space stretching at an ever-increasing rate. De Sitter space is the mathematical description of this pure, dark energy-dominated cosmos, and it possesses a stunning property, maximal symmetry. It is perfectly homogeneous and isotropic on the largest scales, meaning it looks the same in every direction and at every point. More than that, it is scale invariant over time. Its symmetrical geometry remains uniform even as it stretches exponentially. This is the ultimate symmetry of emptiness, a smooth, balanced, and ever-growing void. While our universe is not pure de Sitter space because we still have galaxies and clusters, observations tell us we are accelerating toward that fate. Distant supernovae appear dimmer than they should in a coasting universe, confirming the expansion is speeding up. The cosmic microwave background shows patterns consistent with a large cosmological constant. The evidence is overwhelming. Dark energy dominates the cosmic budget, and its symmetrical push is shaping our destiny. The consequence of this de Sitter symmetry is a future both majestic and lonely. As expansion accelerates, distant galaxies will be carried away faster and faster until their light can no longer reach us. They will cross a cosmic horizon and vanish from view, not by moving away in space, but by space itself stretching so rapidly that their signals are forever lost. In the far future, an observer in our position would see only the stars of their own galaxy, adrift in an immense, dark, and seemingly static void. The universe on the largest scales would appear profoundly featureless and balanced, a realization of that maximal de Sitter symmetry. This presents a deep philosophical contrast. Our local universe is rich with structure, from the spiral symmetry of galaxies to the intricate dance of binary stars. Yet the overarching fate dictated by dark energy is one of increasing uniformity, a smoothing out of all features across cosmic horizons. It is a reminder that symmetry can manifest as both the source of beautiful complexity, like a snowflake, and as the austere, blank canvas of an empty, expanding space. This large-scale, smooth symmetry of dark energy stands in stark contrast to another, more dynamic symmetry rippling through the cosmos, one that carries the news of the most violent events in the universe. The smooth, symmetrical push of dark energy shapes the universe's future, but its past is written in violent, asymmetric collisions. When two black holes locked in a final death spiral merge into one, they do not scream into the void. They ring it. Their cataclysmic union sends ripples through the very fabric of spacetime itself, distortions that travel outward at the speed of light as gravitational waves. In 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, heard this cosmic ring for the very first time, a faint chirp that confirmed a century-old prediction of Einstein's general relativity. But the waves carried more than just news of an event. They carried a precise signature of symmetry in their very structure. Unlike light waves, which oscillate in a single plane with a dipole symmetry, gravitational waves exhibit a quadrupole symmetry. Imagine a circle of marbles on a trampoline. If a mass with a simple back-and-forth motion, like a dipole, distorts the surface, it would stretch and compress the circle into an ellipse along one axis. A quadrupole source, like two masses orbiting each other, does something more complex. It squeezes the circle along one axis while simultaneously stretching it along the perpendicular axis, and then rotates this squeezing and stretching pattern by 45 degrees. This creates two distinct polarization states called plus and cross. As the wave passes through an object, it alternately stretches and compresses space in these two perpendicular patterns, a unique fingerprint of a spinning, asymmetric mass distribution. This quadrupole nature is not an accident. It is a direct consequence of gravity being a spin-2 field. In the language of particle physics, the hypothetical carrier of the gravitational force, the graviton, would have a spin of 2. This higher spin value mandates the more complex quadrupolar pattern of radiation, fundamentally different from the spin 1 photon of electromagnetism. When LIGO detected the signal from those first merging black holes, the observed waveform matched the predictions of general relativity with breathtaking precision. The way the wave's frequency and amplitude increased as the black holes spiraled inward, culminating in the final ring-down of the new, merged black hole, was a perfect symphony of symmetric mathematics played out in the most asymmetric of events. This confirmation is profound. It means that even in the most extreme warping of spacetime near the event horizons of black holes, Einstein's theory and its embedded symmetries hold true. These waves are a new, symmetric probe of the cosmos, allowing us to hear events invisible to traditional telescopes. We are no longer just stargazers. We are eavesdroppers on the universe's deepest vibrations, listening to the symmetric ripples from collisions that happened billions of years ago. This precise mathematical symmetry etched into the fabric of reality itself leads us to wonder, are the rules of this symphony, the very constants of nature, also expressions of a deeper, hidden symmetry? The gravitational waves from colliding black holes confirm a profound symmetry in spacetime's fabric. But what about the fundamental constants that dictate how that fabric is woven? Among all the numbers in physics, one stands out for its eerie constancy and mysterious value, the fine structure constant. Denoted by the Greek letter alpha, this number is approximately 1/137. It is not a measurement of length or time. It is a pure, dimensionless ratio that defines the strength of the electromagnetic force. It governs how tightly electrons are bound to atomic nuclei, the energy levels within atoms, and the very nature of light itself. Its value is a linchpin of reality, setting the rules for all chemistry and biology. The astonishing thing about alpha is its symmetry across the cosmos, a property known as scale invariance in certain contexts. This means that as long as alpha remains fixed, the fundamental processes of quantum electrodynamics, like how an electron scatters light, will look the same regardless of the energy scale or distance involved. It is a key that unlocks similar behavior across different levels of reality. For decades, scientists have tested this constancy with extreme precision. They have measured alpha in laboratory experiments on Earth, and more remarkably, by analyzing the light from incredibly distant quasars. As this ancient light travels for billions of years, it passes through clouds of interstellar gas, which absorb specific wavelengths that act as a fingerprint for atomic structure. By comparing these absorption lines from 12 billion years ago to those measured today, astronomers can check if the fine structure constant has changed. The result, within the limits of our most sensitive instruments, alpha appears to be the same now as it was when the universe was in its infancy. This temporal and spatial invariance suggests a deep and stable symmetry woven into the laws of physics themselves. If alpha were to vary even slightly across space or time, it would represent a catastrophic breaking of that symmetry. The consequences would be staggering. Atomic orbits would shift, the bonds between elements would change strength, and the very stability of matter could be called into question. Stars might not burn, and complex molecules necessary for life might never form. The universe as we know it hinges on this one number staying precisely as it is. This leads to a haunting and beautiful enigma. Why 1 over 137? Why not 1 over 136 or 1 over 140? There is no known fundamental theory that predicts this specific value. It is simply a number we measure. Its constancy points to a symmetric principle, but its specific value remains one of the greatest unsolved mysteries in physics. Some theorists wonder if it is not a constant at all, but the result of a field that settled into its current value during the universe's earliest, most symmetric phase. The unwavering nature of the fine structure constant acts as a silent guarantor, ensuring the laws of physics are the same everywhere and everyone, a perfect symmetry that allows for the consistent unfolding of cosmic history. This unwavering constancy in our current epoch compels us to look back even further, to a time when the symmetries of nature were not hidden but naked and unified, in the unimaginable heat of the universe's first moments. The unwavering constancy of the fine structure constant suggests a universe built on stable, symmetric laws. But to explain that very stability, we must journey back to a time when the cosmos was less than a trillionth of a second old, to a moment of unimaginable symmetry breaking that set everything in motion. This is the theory of cosmic inflation. In its first fleeting instance, the universe is thought to have undergone a staggering, exponential expansion, doubling in size over and over again in a fraction of a blink. During this inflationary epoch, a hypothetical field, often called the inflaton, dominated the energy of the cosmos. Think of this field like a ball perched at the very top of a perfectly smooth, symmetrical hill. This position represents a state of high energy and perfect symmetry, but it is an unstable perch. As the ball begins to roll down into the valley below, it breaks that initial symmetry, choosing a specific direction. This rolling or decay of the inflaton field released an immense amount of energy that reheated the universe, filling it with the hot plasma of the Big Bang and ending the period of inflation. This brief, violent stretch solves profound cosmological puzzles. The most famous is the horizon problem. The cosmic microwave background is uniform to 1 part in 100,000, meaning regions on opposite sides of the sky were once in thermal equilibrium. But in the standard Big Bang model, there was not enough time for light or any influence to travel between them to establish that balance. How did they know to be the same temperature? Inflation provides the elegant answer. Before inflation, the entire observable universe was a tiny, subatomic patch that was causally connected, meaning every part could communicate with every other part. The explosive, exponential expansion then stretched this tiny, thermally balanced region to a size far larger than our entire observable universe today. What we see as opposite horizons were once cozy neighbors, explaining their perfect thermal symmetry, but inflation's most breathtaking gift was the origin of all structure. Even in that primordial, ultra-small patch, the quantum world was alive with fluctuations, a frothing sea of virtual particles popping in and out of existence. Inflation acted like a cosmic magnifying glass, stretching these minuscule quantum jitters across astronomical distances. These stretched fluctuations became the seeds for all future structure, imprinted as tiny variations in density, the very wrinkles we see in the cosmic microwave background. And here lies a profound prediction: the pattern of these primordial seeds should be nearly scale invariant. This means the fluctuations should have roughly equal power, or amplitude, across all different size scales, from the size of a galaxy cluster to the size of the entire observable universe. It is a specific kind of symmetry in the initial conditions. A perfectly scale invariant spectrum would look like a straight, flat line on a graph of power versus scale. The magnificent confirmation came from detailed maps of the cosmic microwave background by satellites like WMAP and Planck. The observed pattern of hot and cold spots matches a nearly scale invariant spectrum with extraordinary precision. It is not perfectly flat, however. There is a slight tilt, a gentle slope indicating that the very largest scales have a tiny bit more power than the smallest scales. This slight deviation from perfect scale invariance is not a flaw, it is a crucial clue. It tells us about the specific shape of that inflationary hill, the properties of the inflattened field itself, and how the symmetry breaking unfolded. So inflation presents a masterful narrative of symmetry in action. It begins with a brief epoch of extreme symmetric expansion that smooths and flattens the universe. This expansion then magnifies underlying quantum symmetries into a cosmic scale invariant pattern. That pattern, a symmetric blueprint written in density, later breaks via gravity to form galaxies, stars, and planets. In this way, a fleeting moment of profound symmetry in the first instance of time became the architect for all the beautiful complexity that followed. This quantum origin story for the cosmos leads us to a final, enduring symmetry, one that governs not mass or energy, but information itself. Information, in its most fundamental quantum form, is the ultimate cosmic currency. It is not just the bits and bytes we store on a drive, but the complete specification of a system's quantum state, the precise arrangement of all its possibilities. In the quantum world, this information is governed by a profound and unbreakable symmetry called unitarity. This principle states that the evolution of any closed quantum system over time is described by a unitary transformation, a mathematical operation that is perfectly reversible and preserves the total sum of probabilities. In essence, it means that quantum information can never be truly created or destroyed, only scrambled and transformed. It is the quantum expression of the conservation of information, a symmetry under time evolution that ensures the universe keeps perfect books. This is not just abstract math, it is the bedrock of quantum mechanics, guaranteeing that if you could perfectly reverse all the interactions of a system, you could, in theory, trace it back to its exact starting point. The implications become staggering when we confront the most mysterious objects in the cosmos, black holes. According to Stephen Hawking's groundbreaking work, black holes are not completely black, they slowly evaporate by emitting a faint glow of radiation. This Hawking radiation, however, appeared to be purely thermal, random heat with no encoded information about the matter that fell in. If a black hole evaporates completely, leaving behind only this featureless radiation, what happened to the quantum information of the stars, planets, or books that formed it? This is the black hole information paradox, a direct clash between unitarity and general relativity that has puzzled physicists for decades. The prevailing resolution, supported by tools like the AD-SCFT correspondence in string theory, suggests that information is not lost. The AD-SCFT duality proposes a remarkable holographic principle that a gravitational theory in a volume of space, like the interior of a black hole, is perfectly equivalent to a quantum field theory without gravity living on its boundary. In this picture, all the information about what fell into the black hole is not stored in its vanished interior, but is meticulously encoded on its two-dimensional event horizon, the surface that shrouds it from view. The evaporation process then scrambles and ultimately releases this information back into the universe through subtle correlations in the Hawking radiation, preserving unitarity. The symmetry holds, but in a deeply non-intuitive way. We see this principle in action today, not with black holes but in laboratories. The entire field of quantum computing relies on unitary operations. Quantum bits or qubits are manipulated through precisely controlled unitary transformations that preserve their quantum information as they perform calculations. Quantum teleportation, the transfer of a quantum state from one location to another, is a direct application of unitary symmetry and the conservation of quantum information. It uses entangled particles and classical communication to reconstruct a state elsewhere, demonstrating that information, not matter, is the fundamental entity being moved. This leads to a breathtaking philosophical possibility. If unitarity is a fundamental symmetry of reality, and all physical processes are ultimately quantum mechanical, then the universe itself could be seen as a vast, ongoing quantum computation. Every interaction, from the fusion in a star to the firing of a neuron, is a unitary transformation in this cosmic quantum computer, with information symmetry as its immutable operating code. This deep quantum symmetry does not exist in isolation. It whispers of a connection to the geometric symmetries of higher dimensional theories, where the fabric of spacetime and the rules of quantum information may be two sides of the same holographic coin. The idea that reality could be a vast quantum computation finds its ultimate expression in a single, breathtaking mathematical object. The E8 Lie group is an abstract structure of staggering symmetry, existing in 248 dimensions. To visualize it is impossible for the human mind, but its mathematical beauty has captivated theorists searching for a truly unified description of the cosmos. In this framework, every known particle and force could be seen not as separate entities, but as different facets or vibrations of this single, symmetrical geometry. Garrett Lissey's exceptionally simple theory of everything is one bold attempt to map the known particles of the Standard Model and gravity onto the intricate lattice of E8. In this proposal, each of the 248 dimensions corresponds to a degree of freedom for a particle or a force carrier. The familiar electron, quarks, photons, and even the elusive graviton would all find their place as points on this grand symmetrical shape. The interactions between particles, the very rules of how they combine and repel, would then arise naturally from the geometry of the group itself, much like the properties of a crystal emerge from its underlying lattice. While this specific model remains highly speculative and faces significant theoretical hurdles, the pursuit it represents is profound. E8 stands as a symbol of the pinnacle of mathematical symmetry, a hint that beneath the apparent complexity of our universe's 4 forces and dozens of particles, there may lie a singular, elegant origin. The diversity we see, from the nuclear glue holding atoms together to the cosmic pull of gravity, might all be the result of that one pristine symmetry breaking in the first moments of time. It is a cosmic version of a snowflake forming, where a perfectly symmetrical water molecule, under the right conditions, crystallizes into a specific, complex, 6-pointed pattern. The E8 group offers a potential master pattern from which all of reality's intricate designs could have crystallized. This quest for a unified symmetric origin is not just about particles in a lab, it is about the architecture of everything. And if such profound symmetry is woven into the laws of physics, we should expect to see its echoes not just in the quantum realm, but in the largest structure we can observe, the cosmic web of galaxies. That single, symmetrical mathematical object hints at a hidden order behind all forces and particles. Yet this underlying symmetry must also manifest in the grand architecture of the cosmos itself, in the distribution of matter on the very largest scales we can observe. Our most detailed maps of the universe reveal a breathtaking structure known as the cosmic web. It is a vast, sponge-like network of brilliant galaxy clusters and glittering filaments woven around immense, dark voids of near emptiness. This is the large-scale structure of the universe, the final product of billions of years of gravitational growth from those tiny seeds in the early cosmos. When astronomers analyze this colossal network, they find a profound property called statistical isotropy. This means that while any single filament or void is an irregular, unique shape, if you average the properties of the entire web over a sufficiently large volume, it looks the same in every direction. The universe on these grand scales has no preferred orientation, no cosmic north or south, no special axis around which everything is organized. This directional symmetry is a powerful confirmation of the cosmological principle, the idea that our place in the universe is not special. The laws of physics and the distribution of matter are statistically uniform when viewed from any location. We discovered this not by looking at a single beautiful image, but through immense, painstaking surveys like the Sloan Digital Sky Survey. By measuring the redshifts of millions of galaxies, astronomers can plot their positions in three-dimensional space, building up a pointillist map of the cosmic web. The statistical analysis of these maps reveals symmetric clustering patterns, a predictable rhythm to how galaxies are spaced apart that holds true regardless of which way you point your telescope. This symmetry did not emerge by accident. It was forged in the first moments of time. The nearly scale invariant quantum fluctuations from the inflationary epoch were stretched across the cosmos, providing the initial symmetric blueprint. Then, over eons, dark matter, guided only by gravity, began to collapse along these subtle ripples. Dark matter's invisible scaffolding formed first, and ordinary matter, the gas that would become stars and galaxies, later flowed into its gravitational wells. This process, simulated in magnificent detail by projects like the Millennium Run, naturally produces a web-like structure that is statistically isotropic. The computer simulations, which start with those symmetric initial conditions and let gravity do its work, produce virtual universes that look uncannily like the one we observe. This match between simulation and reality is a triumphant validation of our entire model of cosmic evolution, from quantum symmetry to galactic majesty. So the cosmic web is more than a pretty picture, it is a historical document. Its statistical isotropy is a direct imprint of the universe's symmetric infancy, a frozen echo of that initial balance now expressed in the clustering of billions of galaxies. It tells us that the same symmetric principles that govern the quantum world also wrote the blueprint for the largest structure in existence. This seamless connection from the quantum to the cosmic naturally draws our focus inward once more, to the symmetrical properties of the fundamental particles that compose this entire grand design. The cosmic web's grand symmetry is woven from threads we cannot see, the fundamental particles themselves. Among these, quarks and leptons arrange themselves in puzzling, elegant patterns known as flavor symmetries. These are the families of matter, 3 generations each of quarks and leptons, each generation heavier and more unstable than the last. The up and down quarks, the lightest pair, exhibit an approximate symmetry that is absolutely vital. Their masses are nearly, though not exactly, the same. This near equality is why protons and neutrons have such similar masses, a delicate balance that allows atomic nuclei to form with stability. If this flavor symmetry were exact, nuclear physics would be far simpler. But if it were completely absent, the complex nuclei that build our world might never hold together at all. The symmetry is broken but gently, and that breaking itself is a clue to a deeper design. This pattern of 3 repeats with the charm and strange quarks, then the top and bottom, each pair heavier and with more pronounced differences. Why 3, and why these specific masses and relationships? The standard model of particle physics has no answer. It simply inputs these values as measured facts. The patterns we see, however, suggest an underlying approximate flavor symmetry, a hint that these particles might be different vibrational states of something more fundamental, or that they arose from a symmetric principle that was fractured as the universe cooled. This points toward ideas like grand unified theories, where all forces merge at incredible energies, or even extra-spatial dimensions, where geometry dictates the properties we observe. The mystery of the 3 generations is one of physics' most tantalizing puzzles, a symmetric riddle written into every atom. Perhaps the most dramatic evidence of this flavor symmetry in action comes from the ghostly neutrino. For decades, the standard model assumed these particles were massless, and each flavor electron, muon, and tau neutrinos was distinct and unchanging. Then experiments revealed neutrino oscillations. A neutrino born with one flavor can, as it travels through space, morph into another. This astonishing transformation is only possible if neutrinos have mass, and if the flavors we label them with are not perfectly aligned with their mass states. It is a direct and beautiful breaking of flavor symmetry, proving there is physics beyond the standard model. The oscillations themselves follow mathematical patterns governed by mixing angles, another set of symmetrical relationships we are struggling to decode. These ethereal particles, changing identity as they fly, are messengers from a more symmetric past, carrying news of a unified law that once governed all matter. From the subtle symmetries of these smallest building blocks, we now find their influence magnified to a cosmic scale in the vast magnetic fields that weave through the emptiness between galaxies. The ghostly dance of neutrinos hints at a hidden symmetry within matter, but across the vast emptiness between stars, another invisible force weaves a symmetrical tapestry of its own. Stretching across tens of thousands of light years, immense magnetic fields thread through the disks of galaxies, their lines of force often tracing the same elegant spiral patterns as the stars themselves. We cannot see these fields with optical telescopes, but we can hear their story through the long, whispering wavelengths of radio waves. When charged particles, primarily electrons, spiral along these magnetic field lines, they emit a faint radio glow known as synchrotron radiation. By mapping this emission with powerful radio telescopes, astronomers have uncovered a stunning truth. These galactic magnetic fields are not chaotic tangles, but often possess a high degree of order and symmetry, coherently aligned over scales that dwarf our entire solar system. This magnetic architecture is sculpted by a cosmic engine called the galactic dynamo. As a galaxy rotates, its swirling, conductive plasma of gas and charged particles acts like a gigantic electrical generator. Small, random seed magnetic fields, perhaps left over from the early universe, get stretched, twisted, and amplified by this motion. Over hundreds of millions of years, this dynamo process can organize a galaxy's magnetic field into a coherent structure, often one that mirrors the grand design of the spiral arms. In many galaxies, the field lines run neatly along the spiral arms, then loop back through the gaps between them, creating a symmetric, large-scale pattern. This is not a perfect, rigid symmetry, but a statistical one, a prevailing order emerging from turbulent chaos. The Milky Way's own magnetic field exhibits this beautifully, with a dominant direction roughly aligned with our galaxy's spiral structure, guiding the flow of interstellar gas and dust. The influence of this magnetic symmetry is profound. These fields provide a skeleton for the interstellar medium, the vast clouds of gas and dust between stars. They help regulate the collapse of these clouds, either supporting them against gravity or channeling material along specific paths, thereby influencing the rate and location of new star formation. They also act as cosmic accelerators and conduits for high-energy particles called cosmic rays, guiding these subatomic travelers across the galaxy. On even larger scales, magnetic fields have been detected spanning entire clusters of galaxies, tracing the filamentary structures of the cosmic web itself. This suggests that magnetic symmetry is not just a local galactic phenomenon, but a fundamental aspect of cosmic structure, woven into the universe's magneto-hydrodynamic history from its earliest epochs. The presence of these ordered fields, born from dynamos and aligned with the majestic shapes of galaxies, reveals a universe where invisible forces obey the same elegant principles of pattern and balance as the visible ones. This deep magnetic order, however, exists within a cosmos that is not standing still, but stretching in a way that itself reflects a profound and simple symmetry. A galaxy's motion tells a profound story of cosmic symmetry. Edwin Hubble's landmark observation in the late 1920s revealed a universe in motion, not of random drift, but of a beautifully ordered retreat. Galaxies are moving away from us, and the farther away a galaxy is, the faster it appears to be receding. This relationship, known as Hubble's law, is elegantly simple. Velocity equals a constant, now called the Hubble constant, multiplied by distance. This is the Hubble flow, and it is the most direct evidence we have for the expansion of the universe, but its true significance lies in the symmetry it reveals. If every galaxy sees all other galaxies moving away with speeds proportional to their distances, then no single point in the universe is the center. The expansion is homogeneous, looking the same from every location, and isotropic, looking the same in every direction. Imagine the surface of a balloon as it is inflated. Draw dots on the balloon to represent galaxies. As you blow air in, every dot moves away from every other dot. An ant standing on any one dot would see all the other dots receding, with the more distant dots appearing to move faster. The ant's viewpoint is not special. It is the same for every ant on every dot. The Hubble flow is our three-dimensional version of this balloon analogy, a symmetric stretching of the very fabric of space. This uniform expansion is mathematically captured by the Friedmann equations, which describe how the scale of the universe changes over time based on its contents, matter, radiation, and dark energy. These equations are themselves rooted in the cosmological principle of homogeneity and isotropy, the same symmetry that Hubble's law so elegantly demonstrates. Measuring the precise rate of this expansion, the Hubble constant, has become one of cosmology's grandest pursuits. Astronomers use two primary cosmic ladders. Type Ia supernova, which have a known intrinsic brightness, act as standard candles to gauge distances to faraway galaxies. The Baryon acoustic oscillations we discussed earlier act as a standard ruler imprinted in the large-scale structure. The results, however, have introduced a fascinating tension. Measurements from the early universe, like those from the cosmic microwave background, suggest one value for the Hubble constant. Measurements from the local, later universe using supernova suggest a slightly higher value. This discrepancy, if it persists and is not due to measurement error, could be a whisper of new physics. It might indicate that the dark energy driving acceleration is not a simple cosmological constant, but something that evolves over time. Or it could hint at a subtle breaking of the perfect cosmological symmetry on the largest scales, perhaps a slight unevenness in the distribution of matter we have not yet mapped. Whether it confirms our symmetric models or forces them to evolve, the Hubble flow remains a breathtaking testament to a balanced cosmos. That simple linear relationship between distance and velocity encapsulates the grand, symmetric growth of space itself, a silent, relentless rhythm underlying all cosmic history. This expansive symmetry of the observable universe, however, emerges from a far stranger and more turbulent realm, the seething, energetic void of the quantum vacuum. The universe's grand expansion unfolds upon a stage that is never truly empty. Beneath the apparent stillness of space lies the quantum vacuum, a seething, dynamic sea of potential. This is not a void in the classic sense, but the lowest possible energy state of a quantum field, humming with a faint, eternal activity known as zero-point energy. Here, pairs of virtual particles and their antiparticles spontaneously flicker into existence, borrowing energy from the vacuum for the briefest instant before annihilating each other, a process governed by Heisenberg's uncertainty principle. This ceaseless activity is not chaotic but bound by profound symmetries. The quantum vacuum obeys Lorentz invariance, meaning its properties look identical to all observers moving at constant speed, preserving the cosmic speed limit of light. It also respects the gauge symmetries that give rise to the fundamental forces, ensuring the laws of physics remain consistent at every point in this energetic void. In a deep sense, the vacuum is the most symmetric state of all, the blank canvas upon which all particles and forces are painted. Yet, from this perfect symmetry, the diversity of the physical world emerges. The Higgs mechanism provides the classic example. In the early universe, the Higgs field permeating the vacuum settled into a stable but non-zero value everywhere. This process, called spontaneous symmetry breaking, is like a pencil balanced perfectly on its tip, a state of high but unstable symmetry. When it falls, it picks a specific direction, breaking the rotational symmetry of the upright position. Similarly, the Higgs field settling broke an electroweak symmetry, giving mass to the W and Z bosons while leaving the photon massless. Crucially, the underlying laws, the equations themselves, remain perfectly symmetric. The vacuum we inhabit today is this broken symmetry state, and it is why particles have the masses they do, allowing atoms and ultimately us to exist. We can even feel the subtle push and pull of this active vacuum. Place two perfectly smooth, uncharged metal plates extremely close together in a vacuum chamber. Classically, nothing should happen, but at quantum scales, the plates restrict the kinds of virtual particle fluctuations that can occur in the space between them compared to the unrestrained fluctuations outside. This creates a slight pressure difference, and the plates are gently pushed together. This is the Casimir effect, a direct, measurable force arising from the symmetric quantum activity of empty space. But this vibrant vacuum holds one of physics' greatest mysteries, the cosmological constant problem. When theorists calculate the expected energy density of the quantum vacuum by summing all these zero-point fluctuations, the result is a number so enormous it would have caused the universe to tear itself apart instantly. Yet, astronomical observations of the universe's accelerating expansion tell us the actual vacuum energy, which we call dark energy, is positive but incredibly tiny, about 120 orders of magnitude smaller than the prediction. This staggering discrepancy is not just a calculation error, it is a profound symmetry problem. Why is the vacuum energy so exquisitely close to zero, allowing for a long-lived structured cosmos? Some theories suggest a hidden symmetry or a cancellation mechanism we do not yet understand, a fine-tuning that makes our universe possible. This vacuum symmetry, therefore, is the silent foundation. Its Lorentz and gauge invariances underpin all particle physics, while its broken symmetries give particles substance. Its faint energy may shape the destiny of cosmic expansion, and its deepest unresolved puzzle connects the infinitesimal quantum world directly to the fate of the entire cosmos. From this foundational symmetry of seeming nothingness, we can now trace a direct line to the majestic, curved geometry of everything. The quantum vacuum's symmetric hum is the foundation upon which the entire geometry of reality is built. That geometry, the very shape of space itself, is our next frontier. We call this the topology of the universe, and its symmetries determine the most fundamental rules of cosmic navigation. Topology is not about the precise curves or angles at a single point, but about the global properties of space, its overall connectivity and shape. Is our universe infinite, stretching forever in all directions, or is it finite but without an edge, like the surface of a sphere? Observations from the cosmic microwave background and the large-scale distribution of galaxies overwhelmingly point toward a universe that is flat, or very nearly so, on the largest scales. A flat geometry possesses a beautiful and familiar symmetry. It is Euclidean. In flat space, parallel lines never meet. The angles of a triangle always add up to 180 degrees, and the rules of geometry you learned in school hold true across the cosmos. This flatness is not an accident. It is a direct prediction of cosmic inflation, which stretched any initial curvature to near zero, leaving behind a maximally symmetric and balanced spatial geometry. But flatness does not necessarily mean infinite. A piece of paper is flat, but you can roll it into a cylinder connecting its edges. The geometry locally is still flat. Parallel lines stay parallel, but the topology has changed. It is now finite in one direction. This is where topological symmetries come into play. Could our universe have a similar, multiply-connected shape? One compelling possibility is a three-dimensional torus, like a giant cosmic donut. In such a universe, if you traveled far enough in a straight line, you would eventually return to your starting point from the opposite direction. This creates periodic boundary conditions, a profound symmetry where the cosmos repeats itself in a regular, lattice-like pattern. If this were true, we might see the same cluster of galaxies, or even a duplicate of our own Milky Way, appearing in multiple different directions in the sky, like facing mirrors creating an infinite hall of reflections. Astronomers have searched for these ghostly symmetric repetitions in the cosmic microwave background and in galaxy surveys, looking for matching circles or correlated patterns on opposite sides of the sky. So far, no convincing evidence has been found. Current data strongly favor a simply connected universe, one without these intricate loops and identifications. Yet, the mere possibility illuminates a stunning idea. The largest scale symmetry of all might be one of repetition, where the entire cosmic tapestry is woven from a single, finite, and elegantly connected thread. The symmetry of geometry does more than dictate whether you could sail around the cosmos. It directly influences what we see. The patterns of hot and cold spots in the cosmic microwave background are acoustic oscillations frozen in time, and their specific size and distribution depend critically on the geometry of space they are imprinted upon. A flat universe produces a characteristic peak in the spectrum of these fluctuations that matches our observations perfectly. This geometric symmetry also steers the universe's ultimate fate. A flat universe, balanced precariously between eternal expansion and eventual collapse, is precisely the geometry that allows for the long, slow evolution of galaxies and life. So we are left with a cosmos that appears flat, simply connected, and profoundly symmetric in its large-scale geometry. This elegant solution, however, opens a door to an even more staggering speculation. If the laws of physics and the constants of nature are expressions of symmetry, and if our universe's geometry is one of balanced simplicity, could there be other realms where different symmetries or different breakings of symmetry have produced entirely different cosmic architectures? The elegant geometry of our cosmos hints at a deeper, more staggering possibility. If our universe's laws and constants are expressions of specific symmetries, could there be other realms where those symmetries broke in different ways, creating entirely different realities? This is the Multiverse Hypothesis, a speculative but compelling frontier where our universe is just one island in a vast archipelago of cosmic possibilities. The idea emerges naturally from two powerful theories we have already explored. Eternal inflation suggests that once inflation starts, it may never truly end everywhere. Instead, it creates a frothing, ever-expanding sea of spacetime where new bubble universes, each with its own Big Bang, constantly nucleate and inflate away from one another. Meanwhile, string theory proposes a landscape of perhaps 10 to the power of 500 possible stable configurations, each corresponding to a universe with a different set of physical laws, forces, and particle masses. In this breathtaking view, the multiverse represents a symmetry not of a single cosmos, but of an ensemble, all possible variations consistent with some deeper, underlying principles may be realized somewhere. Our universe, with its specific fine structure constant and its particular breaking of electroweak symmetry, is simply one possible outcome among a near infinity of others. This perspective offers a radical, if untestable, framework for answering one of physics' most haunting questions. Why do our universe's symmetries appear so exquisitely fine-tuned to allow for complexity and life? If the cosmological constant were slightly larger, galaxies would never have formed. If the strong nuclear force were a few % stronger, hydrogen would fuse into helium too quickly in the early universe, leaving no long-lived stars. The multiverse idea suggests an answer through the anthropic principle. We find ourselves in this particular universe, observing this specific set of symmetries, precisely because these are the conditions that allow observers like us to exist. In universes where the symmetries broke differently, perhaps leading to a rapid collapse or a featureless void, there is no one to ask the question. While this idea remains firmly in the realm of speculation, with no direct observational test yet conceived, it encourages a profound shift in perspective. It asks us to see symmetry not as a unique feature of our home, but as a vast and varied theme played out across an unimaginable cosmic symphony. From this dizzying vista of countless possible worlds, we return to our own with a final, grounding question. In a universe born from symmetry, how does the relentless, one-way flow of time emerge from such timeless, balanced laws? The multiverse idea suggests a landscape of timeless possibilities, but our own reality is defined by a relentless, one-way flow. This brings us to a final, beautiful paradox. The fundamental laws of physics, from quantum mechanics to general relativity, are symmetric under time reversal. If you made a film of two electrons colliding or planets orbiting and played it backwards, the events would still obey the same equations. This time translation symmetry, linked by Noether's theorem to the conservation of energy, means the laws themselves do not change from one moment to the next. Yet our lived experience screams the opposite. We remember the past, not the future. A shattered glass does not reassemble on the floor. We grow older, never younger. This is the arrow of time, and it points in one direction only, from order toward disorder, driven by a quantity called entropy. Entropy is a measure of disorder, or the number of ways a system's microscopic parts can be arranged while looking the same from the outside. The second law of thermodynamics states that in an isolated system, entropy always increases or stays the same. It never decreases. This law is not symmetric in time. It gives time its arrow. Think of a drop of ink in a glass of water. Initially, the ink is concentrated, a state of low entropy and high order. Left alone, it will always spread out, mixing evenly with the water to create a uniform, high entropy state. You would never expect the scattered ink molecules to spontaneously gather back into a single, dense drop. The increase of entropy defines the forward direction of time for all macroscopic processes, from the cooling of your coffee to the burning of a star. So here lies the core tension. The microscopic laws are time-symmetric, but their collective outcome is not. The resolution lies in the initial conditions of our universe. For entropy to increase, giving us an arrow of time, the universe must have started in a state of extraordinarily low entropy. The early cosmos, for all its hot density, was remarkably smooth and ordered, a condition set by cosmic inflation. This was a state of very low gravitational entropy. From that pristine, symmetrical beginning, the only way was toward greater disorder. Gravity took that smooth distribution and clumped it into galaxies and stars, a process that increases overall entropy on a cosmic scale, even as it creates local pockets of dazzling order like a living cell or a spiral galaxy. The formation of every structure, the firing of every neuron that holds a memory, and every cause leading to an effect are all processes that release heat and increase the universe's total entropy. They are passengers on the one-way journey that began with that low-entropy seed. This final discovery encapsulates the nuanced, dynamic role of symmetry. Time translation symmetry guarantees the stability of physical law, the consistency that allows for planets to orbit and life to evolve. Yet, it is the breaking of that symmetry through the thermodynamic arrow, set by a special initial condition, that allows for history, growth, and experience itself. We are creatures of this beautiful asymmetry, our consciousness and our perception of causality flowing along the gradient from a more ordered past to a more disordered future. Having journeyed from the quantum vacuum to the cosmic web, we see a universe where symmetry is not a static perfection, but a generative principle. It provides the unwavering rules, the conserved quantities, and the elegant geometries. But it is in the careful, creative breaking of these symmetries that the cosmos gains its richness, its structure, and its capacity for stories like ours. The deep symmetry of the universe is the silent score, and the unfolding arrow of time is the melody we are here to hear. The universe speaks in a language of balanced relationships, where every whisper of symmetry echoes across the vast scales of existence. From the quantum vacuum's hum to the majestic sweep of galactic arms, these 25 discoveries are not separate notes but chords in a single, resonant symphony. The cosmic microwave background's smooth isotropy set the stage, a symmetrical seed from which all structure could grow. Noether's theorem then revealed this was no accident, tying that smoothness to the unwavering conservation of energy and momentum, the universe's perfect accounting system. This foundational symmetry in the laws themselves gave rise, through gauge principles, to the very forces that would sculpt the cosmos. The photon, the gluon, the W and Z bosons, all are messengers born from nature's demand for local consistency. These forces, in turn, orchestrate the formation of everything, from the crystalline symmetry of a diamond's lattice to the statistical isotropy of the cosmic web. The spiral design of a galaxy, sustained by dark matter's gravitational scaffold and the conservation of angular momentum, is a direct macroscopic echo of those subatomic rules. Even the arrow of time, our one-way journey from past to future, finds its origin in a profound initial symmetry, the low entropy state of the early universe that inflation provided. Each layer of reality rests upon a symmetrical principle from the layer below, creating an interconnected web of breathtaking elegance. This means the weak nuclear force influencing a radioactive decay in a lab is governed by the same symmetrical broken symmetry that shaped the universe's first moments and indirectly allows for the complex atoms in our bodies. The fine structure constant's unwavering value ensures chemistry works the same in a distant nebula as it does on Earth. permitting the same starlight that traces galactic magnetic fields to also power life on a planetary scale. We are not merely observers of these symmetrical threads, we are woven from them. The carbon in our cells was forged in stars whose stability relies on the Pauli exclusion principle, a fermionic symmetry. The electrical impulses in our nervous systems depend on the gauge symmetry of electromagnetism. Our very perception of a consistent, predictable reality is a gift of Lorentz invariance and the cosmological principle. To study cosmic symmetry is, in a very real sense, to study the deepest blueprint of our own existence. It reveals a cosmos that is profoundly unified, where the very large and the very small are in constant, silent conversation through the language of invariant law. This interconnected web transforms our understanding from a catalogue of facts into a story of relationship, a narrative where every discovery, from the Higgs field to the Hubble flow, is a chapter in the same epic of emergent order. Our voyage through 25 scientific discoveries has illuminated a profound truth. Symmetry is the hidden architecture of the universe, governing everything from the quantum foam to the cosmic web. We have traced its fingerprints from the pristine uniformity of the cosmic microwave background to the intricate dance of subatomic particles, from the elegant theorems of Emmy, Noether to the accelerating expanse shaped by dark energy. Each revelation shows us that these symmetries are far more than mathematical curiosities. They are the fundamental rules for conservation, the essential blueprints for all structure, and the tantalizing hints of a deeper, unified reality. In a cosmos that can seem vast and chaotic, a deep and abiding order prevails, written into the fabric of spacetime itself. The physicist Leon Lederman captured this beautifully when he said, "The universe is symmetric, and that symmetry is beautiful." That sentiment resonates through every discovery we have explored, from the perfect Blackbody spectrum of the early universe to the statistical isotropy of the galactic web. It is a beauty not of mere appearance but of profound connection, linking the forces in an atom to the fate of a galaxy. Let this journey inspire you to look at the night sky with new eyes. When you see the band of the Milky Way or the steady arc of a planet, recognize the silent symmetries at work, the conservation of angular momentum in an orbit, the gauge symmetry in the starlight, the cosmological principle in the vast darkness. These are not abstract concepts, they are the very threads that connect us to the stars, the same principles that forged the elements in ancient supernova and that allow our minds to comprehend their light. If this exploration into the universe's deep symmetry has sparked your curiosity, consider subscribing for more journeys into the mysteries of the cosmos. We would love to hear which symmetry fascinates you most. Was it the time translation invariance that gives us a consistent reality, or the broken symmetry of the Higgs field that gives particles mass? Share your thoughts in the comments below. Thank you for joining this expedition into the elegant order of all things. May the wonder it inspires guide your gaze ever onward.